Hello everyone and welcome back. In this session, we are going to learn about the instruction types ADDR, ADI-D8 and INR R. So without any further ado, let's get to learning. Now before we learn about the topics of the day, let me remind you till the previous session, we have covered all the data transfer group of instructions. And specifically in the last couple of sessions, we have concretized all the knowledge that we gained regarding all the different data transfer instructions. I hope you remember that there were 13 instruction types that we learned so far, through which we covered 83 opcodes. Now from this session onwards, we are beginning our journey of learning the arithmetic group of instructions. And before we study them, let me tell you, there are 14 different instruction types that we will cover, and through that, cumulatively we will also learn about 62 different opcodes. So let's get into the topics of the day. Today, we are going to learn about 3 different instruction types, starting with the instruction type ADDR. Next, we will learn about the instruction type ADI-D8. And finally, we will conclude our session by learning about the instruction type INR R. So let's begin with the first instruction type, ADDR. Now coming to the instruction type ADDR, I hope you remember that we already have used it when we were learning about the flags register. This instruction type ADDR, it stands for add the contents of R to accumulator. Now what is this R? By mentioning R, we are generally specifying all the different GPRs and the content of them can be added with the accumulator register. Now I believe you remember our session on the importance of registers. There we learned that if a microprocessor has 2 different registers, we can keep one of the operands in one register, and in that register, after the operation is performed, the result will also be stored. Similarly, in case of 8085, it is essential that whenever we perform a binary operation like addition, well, in other words, any operation which involves 2 operands, so in those cases, one of the operand is bound to be reside inside the accumulator register. And the other operand we can keep anywhere, which will be mentioned by this R. Now, after the operation has been performed, the result of the addition in this specific case will also be stored in the accumulator. Now, let me summarize this entire process for you. When we are performing addition, one of the operand must stay inside the accumulator register and another operand can stay anywhere which will be specified by this R. Now consider the instruction type ADDR. Now what do you think? In which particular category size-wise this instruction will fall into? Well, it is an instruction type which falls under the category of 1 byte long instructions. Now let me tell you what exactly the instructions of these type do. We already have witnessed that. If you remember the session of status or flags register, there we have seen the instruction ADDB or ADDB. Now this instruction we used in order to perform this operation. As you can see, the origin, or we can say one of the operands, was stored inside the accumulator register, and the other operand was stored inside the GPR B. And the execution of this instruction performed this operation, and as I have mentioned earlier, the result, that is 38, remember, when we added these 2 numbers, we got a value which is a 3-digit hexadecimal value, but we already know 8 bits is 2-digit hexadecimal value. So the value 38 will also be stored inside the accumulator after the operation has been performed. Now what about the carry? This will be stored inside the flags register, and that's why we need the flags register. So following this, in our incomplete programmer's view of 8085 microprocessor, we are now going to include the flag register as well. Do remember this, all the different arithmetic instructions are going to affect the content of the flags register. Now we already have seen what ADD-R instruction type does. Let me now show you the different variations of this instruction type. Consider the first instruction, it is ADDA. Now what will it do? Try to understand this. We are adding the content of the accumulator with the content of the accumulator itself. So basically, execution of this instruction will double the contents within the accumulator register. Now after this instruction, in this instruction type that is ADDR, we can also consider all the different GPRs, that is ADDB, ADDC, ADDD till ADDL. Now you must be wondering, in our previous instruction types, specifically in case of data transfer instruction types, after the mnemonic, we had been using small r. Now why exactly we are using capital R in this specific case? Well, the reason for that is, along with all these 7 instructions, we will also consider another instruction, and that is ADDM. Now let me tell you what this instruction will do. We already know whenever we use this alphabet M, it specifies the memory location which will be pointed by the HL register pair. And using this instruction, we can add the content of the accumulator with a specific memory location which will be specified by this M. Inclusion of this instruction within this group made us change the small r notation to capital R. Remember, whenever we are using small r in an instruction type, we are mentioning about the accumulator register and all the GPRs. However, when capital R will be mentioned, it will also mean the memory element which will be pointed by the HL register pair. Now this instruction, specifically add M, can you tell me in which group of addressing mode it will fall under? Well, it is register indirect addressing mode, right? Because in this instruction as well, we are not mentioning anything about the HL register pair directly. However, it is being mentioned indirectly by the use of M. Now earlier I told you the arithmetic instructions are going to affect the content of the flags register. So let me remind you what are the different contents of the flags register. Well, the flags register is also of 8 bits, and the contents from the least significant bit till the most significant bits are, at first we have got CY, that is carry. Then the bit positions 1, 3 and 5, these are don't care combinations. That means the microprocessor doesn't really care what we have stored in these locations. Bit position number 2 is parity. Bit position number 4 is AC or auxiliary carry, and I hope you remember what auxiliary carry is. When we add a 2-digit hexadecimal number with another 2-digit hexadecimal number, the carry coming out from the least significant digits is known as auxiliary carry, and on the other hand, the carry coming out from the addition of the most significant digits is known as the carry. Thereafter, the bit position number 6 is Z or 0. This bit will specify whether the content within the accumulator register after the operation has been performed is all zeros or not. And finally, the bit position number 7 is S or sign. We already know in 2's complement representation, the sign is derived from the most significant bit or the most significant bit position. Following that, this bit, that is the bit position number 7, is specified for sign. So that was a brief recap of the flags register content, and we already have seen the instruction type ADDR. Remember, it stands for add the contents of R. Now by R we mean all the GPRs, the accumulator, also the memory element which will be pointed by HL register pair to the accumulator. And after the addition, the result of the addition will also be stored inside the accumulator. Another thing to note in here, the instruction type add R falls under the category of 1 byte long instructions. So that was all about the instruction type ADDR. Let's now learn about the next instruction type ADID8. Now coming to the instruction ADID8, if you notice, the mnemonic ADI here stands for add immediate to accumulator. So clearly, one operand will stay inside the accumulator register and the other operand we will send via the instruction itself. This D8 specifies the data of 8-bit which we are sending in immediate addressing mode. Now can you tell me in which category size-wise this instruction will fall under? Well, notice the mnemonic ADI will occupy 8-bit and we are sending another 8-bit in immediate addressing mode. So cumulatively it will fall under the 2 bytes long instructions. Now let me illustrate the working of this instruction type. Say within the accumulator register we have one operand, that is F1. And we are going to execute the instruction ADI12H. Now by this we mean this 12 hexadecimal number we are sending to the microprocessor using immediate mode. Now if we execute this instruction, the operand inside the accumulator register will be treated as one of the operands in the addition, and the data of the 8-bit will be treated as another operand. Now if we perform the addition, 1 plus 2 will give us the result 3. And what about F plus 1? I hope you remember the shortcut trick for this. If we add anything with F, that is the largest hexadecimal symbol, in the result we will have 1 less than the addend. So the outcome of this is going to be, at first we will have a carry and the sum is going to be 0. Now once this addition is performed, thereafter the result, that is 03, which is of 8 bits, is going to be stored inside the accumulator register. Additionally, we have got a carry in here. Therefore, in the flags register, the bit position number 0 or the least significant bit is going to be set. So this is how the ADI D8 instruction is going to work. Now do remember, in this instruction type, we only have a single instruction or a single opcode. The opcode will be formed by taking 8 bits or 2-digit hexadecimal numbers for ADI, and the remaining part of the opcode will be specified by this data of 8 bits, that is, 2 more digits in hexadecimal. And that's how the instruction type ADI D8 falls under the category of 2-byte long instructions. And remember, the mnemonic ADI stands for add immediate to the accumulator. So clearly, we are sending one of the operands in immediate addressing mode. Now before we conclude the discussion of the instruction type ADI D8, let me give you some more informations. Initially I told you any arithmetic operation is going to affect the content of the flags register. Now let me show you how this operation is also going to affect all the different contents. We already have seen, due to the presence of the carry bit within the flags register is going to be set. Now what about the next bit, that is P? Well, it is parity and it will depend on the content of the accumulator. Now I hope you remember what this flag will do. Well, parity is to be set, that is P will become 1 if the number of ones in the accumulator after the operation is even. Let's now check what we have inside the accumulator, 0, 3. Now in case of binary, if we think about it, 0 will be 4 zeros. Now what about 3? It is going to be 0, 0, 1, 1. So in the entire content of 8 bits, we have got only 2 ones, and that 2 are the least significant 2 bits. So we have got even number of ones. Due to this reason, the parity bit is also going to be set. Now what about AC flag? As you can see, during the operation, no carry came out of the least significant 2 digits. So auxiliary carry will be reset. Now what about Z flag? After the entire operation, is the content of the accumulator register all zeros? Well, not, right? So therefore, Z flag will be reset to 0. And now what about the S flag, that is the sign flag? Notice the content of the accumulator, 0, 3. Now 0 of hexadecimal is 4 zeros in binary. Clearly, the most significant bit in the accumulator is 0. Therefore, the sign bit will also be reset to 0. So as you can see, this is how all the different contents of the flags register will be affected after any operation is performed, and the result is stored inside the accumulator register. So that was all about the instruction type ADI D8. Let's now learn about the last instruction type for today, that is INR R. Now coming to the instruction type INR R, It stands for increment the contents of R. So we are talking about all the different registers, along with that the memory element as well, because we are considering capital R. Correct? Now the execution of the instruction of this type is going to affect all flags except the CY flag or the carry flag. Now why is that? I'll explain that in a moment. But before that, let me tell you the instruction type INR R also falls under the category of 1 byte long instructions, just like ADDR. Now let me show you how this instruction is going to work. Say we have got the value 03 inside the accumulator. Now if we execute the instruction INR A, the content within the accumulator register, which is currently 03, will then become 04. In other words, the content within the accumulator register was added with 1 or incremented by 1, and then the result was stored inside that accumulator register. Now this will be specific for all the different instruction variations of this type. So we are talking about the instructions INR A, INR B, INR C, to be precise all the GPRs, also INR M. Now remember, after the instructions are executed, the contents within those particular locations, whether that be the accumulator or any of the GPRs or even the memory element, will be updated and will be kept in those locations only. Now I told you the execution of this type of instructions is going to affect all the flags except CY flag or the carry flag. Now let me tell you the reason behind that, and in order to explain that to you, I'll take an example and we are going to execute the instruction INR M. Now say within the memory location F820, we have got the value FF, that is all ones in 8 bits. Now in order to access this memory location, we already know we will have to load this address inside the HL register pair. Now once this is done, then the microprocessor will know that the memory location F820 is being pointed. Now we can go ahead and execute INR M instruction. Now think about the situation. The content is FF, that is all ones in 8 bits. Now if we increment this, what will be the result? If you think about it in hexadecimal, look at the number FF. So it is a 2-digit hexadecimal number, and in both the digit places, we have exhausted the digits by using the largest symbol of hexadecimal. Now if we increment this, in the next number, these two places will be reset, and we will be introducing another digits place which will be set to 1. So in other words, if we add 1 with FF, the next hexadecimal number is going to be 100. But think about it. 100 is a 3-digit hexadecimal number, and the memory location, since these are of 8-bit size, it can store only 2-digit hexadecimal number. So the outcome of the execution of this instruction is going to reset this FF to 00. Now this is the result of incrementation. We are not specifying any addition, right? If we had specified addition, we would have generated the carry. But since it is incrementation, that's why we are not affecting the carry flag. By executing this instruction, the microprocessor is just going to reset the value from FF back to 00. And that's the reason for the instruction type INR R. All flags except CY flag are affected depending on the result. So I believe the concept of the instruction type INR R is clear to you. Remember, INR mnemonic stands for increment, and the instruction type INR R means increment the contents of R. Now by R, we are mentioning all the different registers, including the GPRs and the accumulator, also the memory element which will be pointed by the HL register pair. Additionally, the instruction type INR R falls under the category of 1 byte long instructions. So in this session, we covered the topics: instruction type ADDR, the next instruction type ADI-D8, and the instruction type INR R. ADDR and INR R, these two fall under the 1 byte long category. However, ADI-D8 falls into the 2 byte long category of instructions. Alright people, that will be all for this session. In the next session, we are going to learn 2 more instruction types which are also the part of the addition operation. So I hope to see you in the next one. Thank you all for watching.